So, exceptions. Exceptions indicate that something out of the ordinary or perhaps incorrect has occurred or been detected by the system. This could be as simple as the user misspelling an input file name. It could also be something more difficult to fix, such as the local disk being totally full. The exception mechanism allows the program to deal with the problem in a controlled manner rather than simply crashing. Exceptions can be as simple or as complex as the program design requires. Terminology: exception, object or value that signals an error. Throw an exception, send a signal that an error has occurred. Catch, handle an exception, process the exception, interpret the signal. Keywords: throw, followed by an argument, is used to throw an exception. Try, followed by a block, is used to execute code that may throw an exception. Catch, followed by a block, is used to detect and process exceptions thrown in the preceding try block. Takes a parameter that matches the type thrown. Exceptions flow of control. A function that may throw an exception is called from within a try block. Then, if the function throws an exception, the function terminates and the try block is immediately exited. A catch block to process the exception is searched for in the source code immediately following the try block. 3. If a catch block is found that matches the type of exception that was thrown, it is executed. If no existing catch block matches the type of the thrown exception, then the program terminates. So here we have an example: try, block that calls a function, tot days equals total days, days weeks, cout total days, tot days, end line, catch string message, interpret exception, cout error, message, end line. Example: throw an exception, a function that throws an exception, int total days, int weeks, string message, invalid number of days. If days is less than 0 or days is greater than 7, throw message. The argument to throw is the string object. Else return 7 times weeks plus days. What happens? 1. The try block is entered. The total days function is called. 2. If the first parameter is between 0 and 7, then the total number of days is returned to the caller. The caller outputs the total days message, and the catch block is skipped over. No exception thrown. 3. If an exception is thrown, then the function and the try block are exited. The catch blocks are scanned for the first one that matches the data type of the thrown exception. The catch block executes. Exception not caught. An exception will not be caught if it is thrown from outside of a try block. There is no catch block that matches the data type of the thrown exception. If an exception is not caught, the program will terminate. Clarification: when we say that the throw statement must be executed within the try block, we are referring to the sequence of execution, not whether this throw statement is located within the curly braces of the try block. Very often, the throw statement is in some function that was called within the try block. Exceptions and objects. An exception class can be defined within a class and thrown as an exception by a member function. This is a way to give the exception a descriptive name. An exception class may have no members, used only to signal an error, member variables and functions. In this case, the code that does the throw can pass error data to catch block. A class can have more than one exception class. An example: class invalid pay rate, private double pay rate value, public invalid pay rate, double input, pay rate value equals input, double get invalid pay rate, return pay rate value. Try test pay rate, catch invalid pay rate e, cout invalid pay rate, e dot get invalid pay rate, bool test pay rate double rate. If rate is less than 0, throw invalid pay rate, return true. What happens after catch block? Once an exception is thrown, the program cannot return to the throw point. If the throw is executed inside some function that was called within the try block, then the function terminates, does not return to its caller. Other calling functions in the try block are also terminated, resulting in unwinding the stack. If objects were created in the try block and an exception is thrown, they are destroyed. Nested try blocks. Try-catch blocks can occur within an enclosing try block. Exceptions caught at an inner level can be passed up to a catch block at an outer level. Catch, throw, pass exception up to the next level. Exception summary. Exceptions, a relatively clean mechanism for handling errors in a program. You have throw, try, and catch. Function templates is a pattern for a function that can work with more than one data type. When we write a function template, we specify one or more parameters that represent the data types. When the program includes a call to the function template, the compiler generates code for the specific data types that are used in the function call. An example is template class T. t times 10 t num, return 10 times num. What gets generated when when times 10 is called with an int? Int times 10 int num, return 10 times num. What gets generated when times 10 is called with a double? Double times 10, double num, return 10 times num. Calling a function template. Call a template function as if it were a normal function. The compiler generates the actual code for the function. Int ival equals 3, double dval equals 2.55. Cout times 10 ival displays 30. Cout times 10 dval displays 25.5. Multiple type parameters. A function template can have more than one parameter. Template class T1, class T2. Example, template class T1, class T2. Double MPG T1 miles, T2 gallons, return miles divided by gallons. Overloading a function template. Function templates can be overloaded. A program can have multiple templates with the same name. Each template must have a unique parameter list. Template class T, T sum all, T num. Template class T1, class T2, T1 sum all, T1 num1, T2 num2. Function template notes. A function template is a pattern of text that the compiler does not actually use until it is needed. No actual code is generated until the function named in the template is called. A function template uses no memory in the final executable file unless the program includes some code that calls the function and passes it a real data type. When passing a class object to a function template, ensure that all operators in the template are defined or overloaded in the class definition. All data type parameters specified in template prefix must be used in template definition. Where to start when defining function templates. Templates are often appropriate for multiple functions that perform the same task with different parameter data types. However, developing a complex template from scratch may be difficult. Instead, develop a normal function using the usual data types first. Then, after you get the normal function working, convert it to a template. Add template prefix, convert data type names in the function to a type parameter, i.e. a t-type, in the template. Suppose you needed to create several C++ classes and they were all identical except that they each operate on a different numeric data type. For example, blah blah blah. It could be that we would also need classes called long array, float array, and so on. What about non-numeric data types? Can we make a class template for other non-numeric data types? Yes, but all operations have meaning for all data types. Yes, but not all operations have meaning for all data types. For example, how do you increment a string object? Okay. Practical uses for templates. We have used very simple examples as a means to understand how the mechanics of templates work. Function templates and class templates may appear to a student like a language feature with little practical use. The practical use of templates could occur in a situation where some set of standardized operations must be implemented for many different data types. However, the most immediate reason for understanding templates is to better understand the standard template library. This is the topic that we are doing next. Standard Template Library, STL, an extensive library of generic templates for classes and functions. Categories of templates. Containers, class templates for objects that store and organize data. Iterators, class templates for objects that behave like pointers and are used to access the individual data elements in a container. Algorithms, function templates that perform various operations on elements of containers. Containers, you have sequence containers, stores data sequentially in a fashion similar to an array. They appear to the programmer that they are sequential. Some sequence containers actually use contiguous sequential memory addresses, others do not. Associative containers store data in a non-sequential way that can make it easier to locate particular elements in the container. The array class template. An array object works very much like a regular array, a fixed size container that holds elements of the same data type. Array objects have a size member function that returns the number of elements contained in the object. The array class is declared in the array header file. When defining an array object, you specify the data type of its elements and the number of elements. Examples: array int 5 numbers, 5 integers, array string 4 names, 4 strings. The array class overloads the square bracket operator. This enables a program to access individual elements using a subscript, just as we would with a regular array. Iterators, objects that work like pointers, used to access data in STL containers. 5 categories of iterators. You have forward, can only move forward in a container, uses the plus plus operator. Bidirectional, can move forward or backward in a container, uses the plus plus and minus minus operators. Random access, can move forward and backward and can jump to a specific data element in a container. Input can be used with an input stream to read data from an input device or a file. Output can be used with an output stream to write data to an output device or a file. Similarities between pointers and iterators. Use the asterisk and pointer operators to dereference, both yes. So these are all yes, or at least most of them fully apply. So they use the equal operator to assign to an element. They use the is equals and not equal operators to compare. Use the plus plus operator to increment, minus minus to decrement. Use the plus operator to move forward a specific number of elements. Use the minus operator to move backward a specific number of elements. Defining an iterator. To define an iterator, you must know what type of container you will be using with it. The general format of an iterator definition: container type, iterator, iterator name. Where container type is the STL container type, and iterator name is the name of the iterator variable that you are defining. Iterator examples. For example, suppose we have defined an array object as follows: array string 3 names equals Sarah, William, Alfredo. We can define an iterator that is compatible with the array object as follows: array string 3 : iterator it. This defines an iterator named it. The iterator can be used with an array string 3 object. Iterator begin function. All of the STL containers have a begin member function that returns an iterator pointing to the container's first element. Define an array object, array string 3 names equals Sarah, William, Alfredo. Define an iterator for the array object, array string 3 iterator it. Make the iterator point to the array object's first element, it equals names.begin. Display the element that the iterator points to, cout, asterisk it, end L. Iterator end function. All of the STL containers have an end member function that returns an iterator pointing to the position after the container's last element. First element, begin iterator, element, last element, end iterator. Using the begin end functions. You typically use the end member function to know when your loop has reached the end of a container. Define an array object, array string 3 names equals Sarah, William, Alfredo. Define an iterator for the array object, array string 3 iterator it. Make the iterator point to the array object's first element, it equals names.begin. Display the array object's contents while it. Give me 1 second. One, two, 1, 2. Sorry about that. So, using the begin end functions, you typically use the end member function to know when your loop has reached the end of a container. So we define an array object, array string 3 names equals Sarah, William, Alfredo. Define an iterator for the array object, array string 3 iterator it. Make the iterator point to the array object's first element, it equals names.begin. Display the array object's contents while it not equal to names.end. Cout it and L it plus plus the vector class. A vector is a sequence container that works like an array but is dynamic in size. That is, we can change the size of a vector after it has been created. Overloaded operator provides access to existing elements. The syntax for accessing existing elements of a vector looks like code accessing a regular array. The vector class is declared in the vector header file. Adding new elements to a vector. The pushback member function adds a new element to the end of a vector. Vector int numbers, numbers.pushback 10, pushback 20, pushback 30. Using an iterator with a vector, vectors have begin and end member functions that return iterators pointing to the beginning and end of the container. Create a vector containing names, vector string names, Joe, Karen, Lisa, Jackie. Create an iterator, vector string iterator it defines an iterator that is compatible with a vector string object. Use the iterator to display each element in the vector. For it equals names.begin, it not equal to names.end, it plus plus, cout it and L displays the item that the iterator points to. more iterator functions. The begin and end member functions return a random access iterator of the iterator type. The cBegin and cEnd member functions return a random access iterator of the const iterator type. The rbegin and rend member functions return a reverse iterator of the reverse iterator type. The crbegin and crend member functions return a reverse iterator of the const reverse iterator type. The insert member function. You can use the insert member function along with an iterator to insert an element at a specific position. General format, vector name.insert it, iterator pointing to an element in the vector, value to insert before the element that it points to. And placement of container elements. Member functions such as insert and pushback can cause temporary objects to be created in memory while the insertion is taking place. C++11 introduced a new family of member functions that use a technique known as emplacement to insert new elements. Emplacement avoids the creation of temporary objects in memory while the new object is being inserted into a container. The emplacement functions are more efficient than functions such as insert and pushback. Emplacement of container elements. The vector class provides two member functions that use emplacement. Emplace emplaces an element at a specific location. Emplaceback emplaces an element at the end of the vector. With these member functions, it is not necessary to instantiate ahead of time the object you are going to insert. Instead, you pass to the emplacement function any arguments that you would normally pass to a constructor of the object you are inserting. The emplacement function handles the construction of the object and forwarding the arguments to its constructor. So we started talking about standard template library, an extensive library of generic templates for classes and functions, categories and templates, containers. We discussed the array and vector container classes. Iterators, we introduced the concept of an iterator. An iterator behaves like a pointer to some object in a container. Maps, general concepts. A map is an associative container. Each element that is stored in a map has two parts, a key and a value. To retrieve a specific value from a map, you use the key that is associated with that value. This is similar to the process of looking up a word in the dictionary where the word itself is the key and the definition of the word is the value. Map example. We could define a map in which employee IDs are the keys and employee names are the values. You use an employee's ID to look up that employee's name. So 101, Chris Jones, and so on. The map class. The STL map class represents data as key value pairs. The keys that are stored in a map container must be unique. No duplicates are allowed. The map class is declared in the map header file. Table 1710 contains a partial list of member functions. Defining a map object. Example, define a map container to hold employee ID numbers as ints and their corresponding employee names as strings. Map int string employees. So, and we see an example here. First element of this example, the key is 101 and the value is Chris Jones, and so on. The overloaded square brackets operator. You can use the brackets operator to add new elements to a map. General format, map name, bracket key equals value. This adds the key value pair to the map. If the key already exists in the map, its associated value will be changed to value. Deleting elements in a map. You can use the erase member function to remove a map element by its key. So we create a map containing employee IDs and names, map int string employees. Delete the employee with ID 102, so employees.erase 102. The unordered map class. The unordered map class is similar to the map class except in two regards. The keys in an unordered map are not sorted. The unordered map class has better performance because of the way its elements are organized in memory. You should use the unordered map class instead of the map class if you will be making a lot of searches on a large number of elements and you are not concerned with retrieving them in key order. The unordered map class is declared in the unordered map header file. The multimap class is a map that allows duplicate keys. The multimap class has most of the same member functions as the map class. The multimap class is declared in the map header file. So consider a phone book application where the key is a person's name and the value is that person's phone number. A multi-map container would allow each person to have multiple phone numbers. Sets. A set is an associative container that is similar to a mathematical set. You can use the STL set class to create a set container. All the elements in a set must be unique. No two elements can have the same value. The elements in a set are automatically sorted in ascending order. The set class is declared in the set header file. Examples of the set class. Defining a set container to hold integers, set int numbers. Example, defining and initializing a set container to hold integers, set int numbers equals 1, 2, 3, 4, 5. Elements in a set are unique. A set cannot contain duplicate items. If the same value appears more than once in an initialization list, it will be added to the set only one time. For example, the following set will contain the values 1, 2, 3, 4, 5. So you see that there. If your application requires duplicate elements, then you may need to use the multiset class. Adding new elements to a set, the insert member function adds a new element to a set. Stepping through a set with the range-based for loop. Create a set containing names, so set string names equals Joe, Karen, Lisa, Jackie. Display each element for string element in names, cout element, and line. Using an iterator with a set, the begin and end member functions return a bidirectional iterator of the iterator type. The cBegin and cEnd member functions return a bidirectional iterator of the const iterator type. The rbegin and rend member functions return a reverse bidirectional iterator of the reverse iterator type. The crbegin and crend member functions return a reverse bidirectional iterator of the const reverse iterator type. STL algorithms. The STL provides a number of algorithms implemented as function templates in the algorithm header file. These functions perform various operations on ranges of elements. A range of elements is a sequence of elements denoted by two iterators. The first iterator points to the first element in the range. The second iterator points to the end of the range. The element to which the second iterator points is not included in the range. Categories of algorithms in the STL, a bunch there. Namespaces. Motivation for namespaces. If we were writing a large program that used precompiled software libraries for different commercial vendors, it is conceivable that those software libraries could have some name conflicts. Software vendor A might have a graphics library that includes a class named document. Software vendor B might have a text processing library that includes a class named document. If our program needs to include both libraries, then this name conflict would cause compiler errors for our program. Preventing name conflicts. One way the software vendors could prevent name conflicts of this nature is for each vendor to declare a namespace for all of its code. Software vendor A could declare all of its classes and variables to be part of a namespace called vendor A. Software vendor B could declare all of its classes and variables to be part of a namespace called vendor B. Now, our program has a way to distinguish the two classes. Vendor A, document, vendor B. I think that's pronounced extends. But we'll just say vendor A, document, vendor B, document. Big picture organization of C++ software. Namespaces are another way that we can promote modularity in our programs. We have used functions to group sequences of instructions together. We have used classes to create our own data types and control access to individual variables and functions. We can use namespaces to organize multiple classes into libraries. Declaring a namespace. The syntax for defining a namespace is namespace, namespace name, declarations, and curly braces. The declarations could be as simple as variables or it could be functions or classes. So we have a sample program. Include IOStream using namespace standard, namespace test, int x, y, z, int main, test x equals 10, test y equals 20, test z equals 30. Cout the values are, new line, test x, space, test y, space, test z, and line, return 0. Resolving name conflicts. The next sample program illustrates how namespaces can be used to resolve name conflicts. This is an overly simple example intended to illustrate the concept rather than suggest a real-world use case. So namespace test1 int xyz, namespace test2 int xyz, int main test1 x equals 10, test1 y equals 20, test1 z equals 30, and similar output. The using namespace statement. An alternative approach to qualifying the names of each namespace member is to use the using namespace statement. This statement tells the compiler where to search for a particular identifier if it is not defined in the current scope. We have been making frequent use of this statement throughout the course by including the following statement in our source code files using namespace standard. However, many professional C++ programmers consider this to be an unwise practice because occasionally it can lead to unintended name conflicts. Program E3 demonstrates the statement. Contents of nsdemo.h, namespace demo, class nsdemo, public int xyz, nsdemo test object. Contents of that include IOStream, include nsdemo.h, using namespace standard, using namespace demo, int main test object.x equals 10, test object.y equals 20, test object.z equals 30, cout the values are, and so on. Linked lists. The linked list abstract data type. So a linked list is a set of data structures, nodes that contain references, links to other data structures. Reference is meant in a general way here, not necessarily indicating a particular syntax. Head points to this, points to this, points to this, points to a null pointer. A dynamic data structure. References may be memory addresses or array indices, in C++ usually pointers. A linked list can easily be modified while the program is running. We can add a new node to an existing list. So head points to this, points to this, points to this, points to this, and we're going to add a new node here, points to a null pointer. Linked list versus arrays and vectors. Linked lists can grow and shrink as needed, unlike arrays which have a fixed size. Linked lists are not necessarily stored in sequential memory locations. Linked lists can insert a new node between other nodes easily. Linked list organization. A linked list contains 0 or more nodes. It has a list head, a pointer that contains the address of the first node in the list. The last node links to null pointer. Empty list. If a list currently contains 0 nodes, it is the empty list. In this case, the list head points to null pointer. Head, null pointer. Node organization. A node contains data, one or more data fields, a pointer that can point link to another node. A node may be organized as structure, object, etc. Data pointer. Declaring a node. A linked list can be constructed using structs. Declare a linked list node. Struct list node, double value list node, points to next. Or list node, let's just say asterisk next, because I'm not entirely sure the proper way to pronounce that. As we have already seen with structs, no memory is allocated at the time that the struct is declared. Defining a linked list. Define a pointer for the head of the list. List node asterisk head equals null pointer. Head pointer is initialized to null pointer, indicating an empty list. Null pointer pointer. It is used to indicate end of list. Always test a pointer before using it. Node list asterisk p, while p is not equal to null pointer, and so on. We can also test the pointer itself. While p that, same meaning as example above. Linked list operations. Basic operations. Insert a node at the beginning of the list. Traverse the linked list. Append a node to the end of the list. Insert a node within the list. Delete a node. Delete/destroy the entire list. Steps to create a new node. Allocate memory for the new node. So new node equals new list node. Initialize the contents of the node. New node points to value, or just, new node value equals num. Set the pointer field to null pointer. New node next equals null pointer. Add a node at beginning of list. Basic process. Create the new node as already described. Add the new node to the beginning of the list. If the list is empty, set the head pointer to the new node. Otherwise, set the next field of the new node to point to the previously existing first node of the list, and set list head to point to the new node. The new node is now the new first node of the list. Assume a previously existing list. For the purpose of this discussion, suppose that we already have an existing linked list that contains 3 nodes. Head points to 5, which points to 13, which points to 19, which points to null pointer. Create the new node. List node asterisk new node equals new list node. New node value equals 23. New node next equals null pointer. Link the new node to first node in list. So head points to 5, and now our new node points to 23, which points to 5. Point the new node to the beginning of the list. New node next equals head. Set the head pointer to new node. So head points to our new node. And point the list head to the new node. So head equals new node. The new node is now the first node in the list. Traversing a linked list. Visit each node in a linked list. For each node in the list, perform some tasks such as display the node contents, validate data, etc. Basic process. Set a pointer variable node pointer to the contents of the head pointer. Node pointer equals head. While the node pointer is not null pointer, process the data in the node, perform some task. Go to the next node by setting node pointer to the next field of the current node in the list. Node pointer equals node pointer next. Traversing a linked list. Head points to 5 and node pointer is pointing to 5. First, the node pointer variable points to the node containing 5. Process the node containing 5. Modify node pointer to point to the node containing 13. Process the node containing 13. Modify node pointer to point to the node containing 19. Process the node containing 19. Because the next field in the node containing 19 is null pointer, that means the traversal is complete. Appending a node. Sometimes the program may need to add a node to the end of the list. Basic process. Create the new node, as already described. Add node to the end of the list. If list is empty, set head pointer to the address of this new node. Otherwise, traverse the list to the end and set the next field of the last node to point to new node. Appending a node. At the end of the traversal, node pointer points at the last node. Pretty straightforward. The new node has been prepared for linking to the rest of the list. Link the last node of the list to new node. So now 19 is pointing to our new node. Caution about appending a node. Always keep in mind the requirements of your current assignment. If your intention is to maintain a list that is always sorted, then a misused append operation could violate that policy. In such a case, using append could be inappropriate unless you know that the input data is already sorted. Inserting a node within a linked list. Sometimes it is useful to maintain a linked list in sorted order. Suppose we need to maintain the list so that the data values are in ascending order. Requires 2 pointers to traverse the list. A pointer to locate the first node with a data value greater than the value to be inserted. Another pointer to follow behind the first pointer by 1 node so that it will finally point to the node before the point of insertion. The new node is inserted between the nodes pointed at by these pointers. Inserting a node. As node pointer traverses the list, previous node is always behind by 1 link. So head points to 5, points to 13. The previous node is pointing to 13, which is pointing to 19, and our node pointer is pointing to 19, which is pointing to a null pointer. New node is 17, which is pointing to a null pointer. Null pointer. Finally, node pointer points at a node with a data value greater than the data in new node. Adjust the link so that the new data is in the previous location. The sorted order of the linked list has been maintained. Deleting a node. Used to remove a node from a linked list. If the list uses dynamic memory, then delete node from memory. Requires 2 pointers. 1 pointer to locate the node that must be deleted, and another pointer that points to the node immediately preceding the node to be deleted. Prepare for node deletion. First, we need to locate the node we wish to delete, but also maintain a pointer to the previous node. So head points to 5, previous node is pointing to 5, which is pointing to 13, and our node pointer is pointing to 13, which is pointing to 19, which points to null pointer. Unlink the node. The traversal proceeds until the node to be deleted is found. And then we adjust the pointers around the node to be deleted. So 13 is the one to be deleted, so now we're making 5 point to 19 instead of 13. Then we delete the node. Linked list after deleting the node containing 13. Destroying a linked list. Must remove all nodes used in the list. To do this, use the list traversal to visit each node. For each node in the list, unlink the node from the list. If the list uses dynamic memory, then free the node's memory. Set the list head to null pointer. Variation of the linked list. Some linked lists have forward and backward links. Doubly linked list. Each node contains 2 pointer fields, one to the next node in the list, one to the previous node in the list. So head is 5, which has 1 null pointer and 1 pointer to 13, which has 1 previous pointer to 5, and 1 next pointer to 19, which has a previous pointer to 13, and a next pointer to null pointer. Circular linked lists. Some linked lists have a pointer from the tail back to the head. Circular linked list. The last node in the list points back to the first node in the list, not to null pointer. Special tail nodes as a head. So 5 points to 13, which points to 19, which points to a null pointer, and also tail is 19. The STL list container. Template for a doubly linked list. Member functions for locating beginning, end of list, front, back, end. Adding elements to the list, insert, merge, push back, push front. Removing elements from the list, erase, pop back, pop front, unique. The STL also includes a singly linked list container, forward list. Great. Stacks and queues. Part 1, stacks. Introduction to the stack, abstract data type. Stack, a LIFO, last in, first out data structure. Examples are plates in a cafeteria, return addresses for function calls. Implementation, static, fixed size, implemented as array. Example, int stack class, pages, blah. Dynamic variable size, implemented as a linked list. And again, static stack is fixed size and implemented as array, and a dynamic stack is a variable size implemented as a linked list. A last in, first out data structure. Last in, first out. The most recent item placed on the stack will be the next item to be removed. Think of a stack of plates in a cafeteria. Stack operations and functions. Operations: push, add a value onto the top of the stack. Pop, remove a value from the top of the stack. Functions: is full, true if the stack is currently full, i.e. has no more space to hold additional elements. Is empty, true if the stack currently contains no elements. Stack operations: push example. A stack that can hold char values. Push E, so makes sense. Pop example. Dynamic stacks: grow and shrink is necessary. Can never be full as long as dynamically allocated memory is available. Implemented as a linked list. Implementing a stack. Programmers can write their own routines to implement stack functions. These are 2 examples from the textbook. And sample code dynamic int stack. Program 19.4 uses dyne_int stack class. A stack template. The dynamic stack class template supports creating a stack of any data type. The STL stack container. Stack template can be implemented as a vector, a linked list, or a DQ. Implements push, pop, and empty member functions. Also implements other member functions. Size is the number of elements on the stack. Top, reference the element on top of the stack. Defining a stack. Defining a stack of chars named cstack implemented using a vector. Stack char vector char cstack implemented using a list. Stack char list char cstack implemented using a dequeue. Stack char cstack. Older compilers required spaces between consecutive symbols to avoid confusion or operators. Got you. So STL stack member functions. Empty returns true if the stack is empty. Pop removes elements from top of stack. Push X pushes element X onto the stack. Size, number of elements in the stack. Top returns a reference to the element at the top of the stack. Note, the pop function does not retrieve the value from the top of the stack, it only removes it. To retrieve the value, you must call the top function first. So we have a STL stack demo. So we have to include STL stack using namespace standard int main. Const int max equals 8. Int count is the loop counter. Stack int vector int I stack for count equals 2. Count less than max. Count plus equals 2. Cout pushing count and line I stack dot push count. Display the size of the stack. The size of the stack is iStack.size and L. Pop the values of the stack for count equals 2, count less than max, count plus equals 2. Cout popping iStack.top and line iStack.pop. Output from program. So that, and then project description. Stacks and queues part 2. Queues. Introduction to the queue abstract data type. Queue, a FIFO, first in, first out data structure. Examples, people in line at the supermarket cash register, print job sent to a printer. Implementation, static, fixed size, implemented as array. Dynamic, variable size, implemented as linked list. Different from a stack. Stack is a LIFO, last in, first out data structure. Queue locations and operations. Locations, rear, position where elements are added. Front, position from which elements are removed. Operations, enqueue, add an element to the rear of the queue. Dequeue, remove an element from the front of a queue. Dequeue operations, example, a currently empty queue that can hold char values. NQE, front is E and the rear is E. If we NQ K, then the front is E and the rear is K. If we NQ G, then the front is E and K and then the rear is G. If we do DQ, it removes the E from the front and moves K up to the front, and so on. DQ issue solutions. When removing an element from a queue, the remaining elements must effectively shift to the front. If the queue is implemented using an array, then coding this can be a bit tricky. Possible solutions. Let front index move as elements are removed, works as long as rear index is not at the end of the array. Use above solution and also let rear index wrap around to the beginning of the array, treating the array as circular instead of linear. Of course, this added feature means the code for the NQ and DQ operations is a bit more complicated. Dynamic queues. Like a stack, a queue can be implemented using a linked list. Allows dynamic sizing, avoids... Sorry, I just thought of something funny. It's random. Dynamic queues. Like a stack, a queue can be implemented using a linked list. Allows dynamic sizing, avoids issue of shifting elements or wrapping indices. So front and rear. Implementing a queue. Programmers can write their own routines to implement queue operations. See the dyne int queue class in the book. For an example, queue template. The dynamic queue class template supports creating a queue of any data type. The STL DQ and queue containers. So DQ, a double-ended queue, pronounced, or I see it, DEQ, is a double-ended queue. Has member functions to enqueue, pushback, and dequeue, pop front. Queue, container ADT that can be used to provide a queue implemented using a vector list or dequeue or DEQ. The queue container has member functions to enqueue, push, and dequeue pop. Defining a queue. Defining a queue of chars named CQ implemented using a using a DEQ. DEQ char CQ implemented using a queue. Queue char CQ implemented using a list. Queue char list char CQ. Older compilers required spaces and, same thing. Recursion. Introduction to recursion. This function contains a call to itself. Void countdown int num if num is equal to 0. Cout blast off else. Cout num new line. Countdown num minus 1 is the recursive call. We call this function a recursive function. What happens when called? Each time a recursive function is called, new instances of the calling parameters and local variables are created. Each execution of the function has its own local view of the local variables. When a function finishes executing, it returns to the next statement after the statement that called it. With recursion, this is often a different execution of the same function. That is, the calling function has its own copies of the local variables that are different from the local variables in the called function, even though it may be the same source code. When the recursive function finally returns to its original caller, execution continues from that point. Recursive processing example. Suppose the program contains the following statement: countdown 2. 1. Countdown 2 generates the output 2, then it calls countdown 1. Countdown 1 generates the output 1, then it calls countdown 0. Countdown 0 generates the output blast off, then returns to countdown 1. Countdown 1 returns to countdown 2. Countdown 2 returns to the original calling function. Recursive function calls. Okay. This is drawn crazily. Let's try to understand it, right? So first call to countdown num is 2. Countdown 1. Second call to countdown, so the output is 2, Second call to countdown num is 1. Countdown 0, so 1, Third call to countdown num is 0, so no recursive call, blast off. Recursive function returns. First call to countdown 2. Okay. It's pretty straightforward for at least this example. Recursive functions purpose. Recursive functions are used to reduce a complex problem eventually to a problem that is simpler to solve. The simpler to solve problem is known as the base case. Recursive calls stop when the base case is reached, stopping the recursion. A recursive function must always include a test to determine if another recursive call should be made or if the recursion should stop with this call. In the sample program, the test is if num is equal to 0. Void countdown int num if num is equal to 0. Test for base case. Stopping the recursion. 3. Recursion uses a process of breaking a problem down into smaller problems until the problem can be solved easily. In the countdown function, a different value is passed to the function each time it is called. Eventually, the parameter reaches the value in the test and the recursion stops. So stopping the recursion, our countdown num minus 1. Note that the value passed to recursive calls decreases by 1 for each call. Can you see the bug in this function? Void countdown int num. So if num is equal to 0, cout blast off, else cout num new line, countdown num minus 1. So yeah, a negative value. What input would cause trouble? What would the symptoms of the problem be? It would just keep on going. Can you suggest a code change to guard against this occurrence? Yeah, you can do if num is less than or equal to 0. Types of recursion. Direct. A function calls itself. Indirect. Function A calls function B, and function B calls function A. Function A calls function B, which calls function C, which calls function A. Indirect recursion is less obvious to a person reading the code than direct recursion. Always be sure that your comments clearly state what is going on. The recursive factorial function. You may remember the factorial function from one of your mathematics courses. In math textbooks, the factorial function is often expressed using the exclamation mark. N factorial equals n times n minus 1 times n minus 2 times and so on till 3 to 2 to 1 if n is greater than 0. N factorial equals 1 if n is equal to 0. We can easily compute factorial of n if the factorial of n minus 1 is known. So n factorial equals n times n minus 1 factorial. N factorial equals 1 if n is equal to 0. The case where n equals 0 is the base case. The recursive factorial function, int factorial int num. If num is greater than 0, return num times factorial of num minus 1, else return 1. Recursive linked list operations. Remember in chapter 18 how we implemented linked lists. Each node of the linked list is a struct that contains a link to the next node of the list. Declare a structure for the list, struct list node, int value, struct list node, asterisk next. Previously, we used a loop to implement linked list operations. We've seen that many operations on a linked list can be implemented using a loop. However, many linked list operations can also be implemented using recursion. Examples of linked list operations that can be implemented using recursion: compute the size of number of nodes in a list, compute the total of all data values in the list, traverse the list in reverse order. Counting the nodes in a linked list uses a pointer to visit each node. Recursive algorithm. Initially, the pointer starts at head of the list. If the next pointer is null pointer, return 0 base case. If the next pointer is not null pointer, use a recursive call to advance to the next node. After returning from the recursive call, return 1 plus whatever value the recursive call returned. That is, each return value is the length of the remaining list plus 1. Contents of a list in reverse order. If you have a singly linked list, then displaying the list contents in reverse order would be more complicated without using recursion. Recursive algorithm. Initially, the pointer starts at head of the list. If the pointer is null pointer, return base case. If the pointer is not null pointer, use a recursive call to advance to the next node. After returning from the recursive call, display the contents of the current node. Recursion versus iteration. Benefits. Plus, disadvantages, minus of recursion. Plus, So so a pro, let's say, models some algorithms most accurately. Pro results in shorter, simpler functions. Con may execute very slowly because of a function called overhead. Con often uses more memory because of local variables that are present for each level of recursion. Benefits, disadvantages for iteration. Pro usually executes more efficiently than recursion. Con sometimes harder to write or understand the code. If an algorithm is inherently recursive in nature, then a non-recursive implementation of the algorithm may be more complicated. Recursion summary. Any recursive function or program must have a base case to avoid an effective, endless loop. The recursive logic must eventually reach the base case. That is, each recursive step should bring the program closer to the base case. Recursive algorithms are often less efficient than their iterative counterparts. The choice to use a recursive algorithm is usually based on simplicity. Okay, so I made it through, as you can see at the top, and I'm just me double checking. I'm about to take a quiz on chapters 16 to 20. We made it through all that, so that's funny. I just got rhinoceros social behavior here. You can go ahead and guess why that might be. But anyway, peace.